This is Dr. Karthika from the Department of Biomedical Engineering, SNS College of Technology, Coimbatore. Today we are going to discuss about smoothing and sharpening frequency domain filters in biomedical image processing. First of all, we are going to study about image enhancement, spatial domain and frequency domain, basic steps in frequency domain, smoothing and sharpening. Okay, first of all, what is image enhancement? We know that image enhancement is the process of making images more useful for the purpose of highlighting interesting details in images, removing noise from images, making images more visually appealing. For that purpose, we are using image enhancement techniques. Okay, here we have two types of image enhancement. One is a spatial domain technique, another one is frequency domain technique. In spatial domain technique, we have to manipulate pixel intensity directly. In frequency domain technique, we can modify the images with the help of Fourier transform. Okay, in spatial domain technique, here the direct manipulation of image pixels is done, and in frequency domain technique, the manipulation of Fourier transform or weighted transform of an image is used. Okay, here it shows the frequency domain filtering steps. First of all, our input image f of x comma y, it is fed into the pre-processing. After pre-processing the image is fed into the Fourier transform. Here we have two components, one is u and another one is v. It denotes the image properties as well as the image axis here. Okay, next this is moved into the filter function h of u comma v. After that we apply inverse Fourier transform. Here the process is we can multiply h of u comma v with f of u comma v. Okay, the input image and the filter function both are get manipulated and fed into the inverse Fourier transform. After that, the post processing is done. The final enhanced images g of x comma y, this image, it gives the high contrast, high quality image. Okay, and this is about basics of filtering in the frequency domain. Here, first one is multiply the input image by -1 of xy to the center of the transform to u equal to m by 2. Here the mid value is m and v equal to n by 2. If m and n are even numbers, then the shifted coordinates will be integers. The second one is compute f of u comma v and the DFT of discrete Fourier transform of the image from 1. After that, multiply f of u comma v by a filter function h of u comma v, and then compute the inverse DFT of the result in third and it is obtained by third step. After that, obtain the real part of the result in 4. After that, finally multiply the result in 5 by -1 x comma y to cancel the multiplication of the input image. After that, finally we have the required output image. Okay, here we mainly concentrate on high pass filters and low pass filters. The relationship between blurring mask and derivative mask with a high pass filter and a low pass filter, it can be defined simply as blurring mask, are also called as low pass filter, and derivative mask, it is also called as high pass filter. Okay, in blurring mask, all the values in blurring mask are positive only. The sum of all the values equal to 1. The edge content is reduced by using blurring mask, and the size of the mask grow, more smoothing effect will take place in the input image. Okay, while coming to derivative mask have positive as well as it has negative values. The sum of all the values in a derivative mask is equal to 0. The edge content is increased by a derivative mask. As the size of the mask grows, more edge content is increased here. Okay, here we have a input image, we have an example image. Here the inner circle, it shows the low pass filter, and the external, the outer circle, it shows the high pass filter. Okay, here we use some filters for smoothing purpose as well as sharpening purpose. Okay, and for smoothing purpose we use ideal low pass, Butterworth low pass and Gaussian low pass. For sharpening we use ideal high pass, Butterworth high pass and Gaussian high pass. Okay, here this flow chart, it shows the frequency domain filters, low pass filters as well as sharpening filters here. In low pass we have ideal low pass, Butterworth low pass, Gaussian low pass, and in sharpening we have ideal high pass, Butterworth high pass and Gaussian high pass filters. Okay, while coming into smoothing, blurring, it is achieved in the frequency domain by high frequency attenuation. It is achieved normally by using low pass filtering. Here we consider three types of low pass filters: ideal low pass filters, Butterworth low pass filters and Gaussian low pass filters. These three categories, it covers the range from very sharp ideal to very smooth Gaussian filtering. Okay, while moving to frequency domain filters, the Butterworth filter, it has a parameter, it is called as filter order. For high order values, the Butterworth filter approaches the ideal filter. For low order values, Butterworth filter is more like a Gaussian filter. Thus, the Butterworth filter may be viewed as providing a transition between the two extremes. Okay, in low pass filter, most of the basic filtering operations are done by low pass filter. The low pass filter is also called as blurring or smoothing filter. The simplest low pass filter is just calculates the average of a pixel and all its 8 immediate neighbors. Low pass is also called as blurring mask. Okay, ideal low pass filter. Here the formula for ideal low pass filter, it is defined as d of u comma v, it is equal to u minus p by 2 the whole square plus v minus q by 2 the whole square by 1 by 2. Here d naught, it is a positive content and d of u comma v is the distance between the point u comma v in the frequency domain and the center of the frequency, a rectangle. Okay, next one is ideal low pass filters. This ideal low pass filters is it is rarely symmetric about the origin, which means that the filter is completely defined by a radial cross section. While rotating the cross section by 360 degree, it yields the filter in 2D, two-dimensional. For an ideal low pass filter ILPF, a cross section, the point of transition between h of u comma v equal to 1 and h of u comma v equal to 0 is called the cutoff frequency D0. Simply cut off all the high frequency components that area at a specified distance d0 from the origin of the transform. It changes the distance, also change the behavior of the filter. Okay, here this slide, it shows the Butterworth low pass filter. Here the formula is h of u comma v is equal to 1 by 1 plus d of u comma v divided by d0 whole to n. Here the transfer function of a Butterworth low pass filter of order n with cutoff frequency at a distance d0 from the origin is defined here. Normally, the Butterworth low pass filter is a type of signal processing filter. It is designed to have a flat frequency response as possible in the pass band. Okay, here we have a perspective plot of a Butterworth low pass filter with a transfer function, and second one, it shows the filter displayed as an image, and a third one, filter radius cross section of orders 1 through 4 is displayed here. Okay, while coming into Gaussian low pass filters, the transfer function of a Gaussian low pass filter, it is defined as h of u comma v is equal to e power minus d of u comma v divided by 2 sigma. The plots are shown here, shown below. The main advantage of a Gaussian low pass filter over a Butterworth low pass filter is that we assure that there will be no ringing effects no matter what filter order we choose to work with. Okay, Here it shows different low-pass Gaussian filters used to remove blemishes in the image. Normally we use filters in camera. Same concept is applied here. Okay, while move on to sharpening. From smoothing, the edges and fine detail characterized by sharp transition in image intensity has took place, and such transitions contribute significantly to high frequency component of a Fourier transform. Also, it attenuates certain low frequency components, and preserving high frequency components results in sharpening edges and sharpening the image. Okay, sharpening filter transfer function, it is defined as h of hp of u comma v, that is equal to 1 minus hlp of u comma v. When high pass filter attenuates frequencies, low pass filter passes them. When low pass filter attenuates frequencies, high pass filter passes them. Okay, here it shows high pass components, pass components, high pass frequency components, and low pass frequency components. The low pass frequency components, it denotes smooth regions here. Okay, ideal high pass filters. This is a common example of high pass filter. When 0 is placed inside, we get edges, which gives a sketched image. An ideal low pass filter in frequency domain is given below. See this example. We can clearly understand the concept from this image. Okay, here it shows the Butterworth high pass filters. The transfer function is h of u comma v, it is equal to 1 by 1 plus d naught divided by d of u comma v power 2n. Already we have discussed about this, where n is the order and d naught is the cutoff distance as before. Okay, here consider this example image. In the left side, the results of the Butterworth high pass filtering of order 2 with the d naught equal to 15, and the right side, the results of the Butterworth high pass filtering the order 2 with d naught equal to 80. Here the distances varies. Okay, in the upper side we have a clear image. In the lower side, the results of Butterworth high pass filtering of order 2 with the d naught equal to 30. Here the distance matters. Okay, Gaussian high pass filter, it has some concept as ideal high pass filter, but again the transition is more smooth as compared to the ideal one. Okay, while move on to the Laplacian, here it is defined as del square, it is equal to del dot del, it is equal to dou by dou x, dou by dou y multiplied with dou by dou x, dou by dou y, it is equal to dou square by dou x square plus dou square by dou y square. Dot product is applied here. And while using Laplacian mask, we can detect zero crossings, as well as the aim of the image enhancement using this kind of filters is to improve the information in images for human viewers, or to provide better input for their automated image processing techniques. Here, there is no general theory for determining what is good image enhancement when it comes to human perception. If it looks good,